In this video, we're going to talk about one of the coolest applications of LSTMs, maybe the application that really justifies LSTM's existence, and that is sequence-to-sequence models. It's also what Google now uses to do its translation system. They had an amazing blog post last year where they talked about replacing tons and tons of lines of code with a small sequence-to-sequence model that was just trained on lots and lots of data. So the canonical example, not the only example, but the one people think of when they think of sequence-to-sequence models is translation. And I think if you haven't seen this before, you might even wonder, how do translation models work at all, right? So if I have input that says, my name is Lucas, that's an arbitrary length string. And then maybe I want as output the Japanese string, watashi no namae wa Rukasu desu. And that's a totally different length. In fact, it's a different language that doesn't even have spaces. What's going on here, right? The API of machine learning, I keep telling you, is this sort of fixed length input and fixed length output. And here, neither the input nor the output is fixed length. And I think because of that, it took a really long time to make really good translation models. But sequence-to-sequence absolutely nails this. So let's see how it works. And I'll give you a little bit of warning. There's actually a really funny blog post that we should definitely link to in the comments where it calls sequence-to-sequence the clown car of deep learning. And I think that sort of shows that this feels kind of counterintuitive at first, but it really does work super well with enough data. And I always looked for kind of examples that would be fun for students, because a lot of these sequence-to-sequence models take massive amounts of data before they're interesting. And I actually found one in a set of Keras tutorials that I modified for this class. So in this case, our task is to do arithmetic, but with neural networks. So our input data is going to be a really simple equation, and then our output data is going to be the number that equation solves to. So I'm talking really simple. It's going to be like 10 plus 12 as our input, and then our output is 22. But what's kind of amazing here is we're going to treat this as a string-to-string translation problem. So the network has no idea what these symbols mean. It even has to learn that it should be outputting a number, right? So there's nothing that tells it can't output 1 minus 4 or 1 4 minus minus minus, right? That would all be legal in this case. But our input is going to be strings, and our output is going to be strings, and we're going to see if it can learn this task. The way it's going to work is we're going to take our character inputs and we're going to put them in a character encoding. And we're going to pad out that encoding to be the length of the longest input. So because I think we have 12 or 13 possible characters here, the length of the encoded vector is going to be around 12 or 13, and with each cell in that vector corresponding to a different character that we have in our input and our output. And then we're going to feed that into our LSTM, just like we saw in our text generation LSTM example. And that LSTM is going to output a single vector that's going to try to encode somehow the state of our input. And the length of that vector is a configurable parameter, like the hidden dimension of the LSTM. And we're going to take that vector and we're going to do a layer we haven't seen before in Keras, which is called repeat vector, which basically takes that vector and uses it as input for every single step in the next layer in this network, which is another LSTM. And this is like our output LSTM. So this basically takes in a repeated vector as input, and then it tries to output a whole bunch of different numbers. So that's our output LSTM. And our output LSTM now is going to have to output every number in its system, and it's going to pass that into a time-distributed dense layer. So what does that mean? We're basically going to take our dense layer, which right? That's like a perceptron with multi-dimensional output. And in this case, the exact dimension of the output is going to be the number of characters that we have, because it's going to output one hot character encodings. But it's going to have to do that for each character that we want to output. So we're going to have to what's called time distribute the dense layer. And that means that we're going to make as many copies of it as we want outputs. So each one of these perceptrons is going to have the same set of parameters, but we're going to run it on each of the outputs of our output LSTM. And so finally, we're going to get a whole bunch of vectors where each vector corresponds to a character in our output. And then we're going to train this whole system in the same way that we train all the other systems, where we're just trying to make our output as close as possible to the labeled output that's in our data set. And it's really easy for us to generate a lot of data for this quickly because we can actually use a computer or even like a calculator to do this really simple math. But we're going to convert these input and these output things into strings that our network is going to try to understand. So let's go to the code and see specifically how it works. Okay, so in the code, go to mlclass/videos/sequence2sequence, and then open up train.py. And this is some code that I got from an excellent blog post on the Keras blog, a 10-minute introduction to sequence learning in Keras, but I actually modified it to make it a little bit more complicated and hopefully a little bit more understandable. But if you want to learn more, you should definitely go to that blog post also. So as usual, the first couple lines are just import statements and setting up W and B so that we can get a log of our training. And then this code defines what's called a character table. And really this is just a convenience wrapper to make it easy to encode these integers and then decode these integers. So it basically gives us an encode function that does a one-hot encoding of a given string, and then a decode that takes an output from, say our neural network and writes it out as a string that we can understand. So lines 44, 45, 46, and 47 are basically configuration parameters. And one important one here is training size. So that's how many training data points we're going to generate. And we could generate more if we wanted to. But this is going to be our complete data set when we train our model. And then digits corresponds to the longest digit that we're going to allow in our input. So we're going to have up to 5-digit inputs. And because we're only going to do plus and minus in this example, the maximum length of our input is 2 times the maximum size of digits plus 1. Because you could have maybe 10,000 plus 10,000 would be an example of the longest possible input that's allowed. And then line 54, we basically write down all the characters we have. So this is all the digits plus a plus and a minus, and then also a space for padding. And then we initialize our character table with those characters. Now, line 57 through 79 basically automatically generates these input and output strings. So we're basically calculating very, very simple arithmetic like 10 plus 12 equals 22, and we're randomly generating these numbers and then recording the output. And then lines 84 through 89 take that output and it encodes them into X and Y. It basically one-hot encodes them into these vectors that we need to use for input and output into our neural network. Lines 93 through 96 basically shuffle the X and Y. And then lines 99 through 101 does a test train split. And in this case, we use 90% of the data as training data and 10% of the data as validation data. Now here we set up our model, and it should be just like the diagram that I outlined, but here it is in Keras code. So it's a sequential model. Line 104 sets up the encoding LSTM, and this has a hidden size configuration for the number of outputs of its state. And you could definitely play with this. Line 105 is a new type of layer, the repeat vector layer, which basically takes the output of this LSTM and makes copies of it, enough copies to feed in to the next LSTM down. And this LSTM is actually going to try to output the digits that we want. So we actually have to set return sequences equals to true, which is something you might remember from a previous video, which makes it so the LSTM doesn't just output its final state, but outputs every intermediate output state. And we need this because in this case, we're not just trying to classify something, we're trying to output an entire sequence of digits corresponding to the answer. Then in line 107, we take a dense layer, and the dense layer outputs a vector of the length of the number of characters, because we can interpret this as essentially a one-hot encoded answer to what character occurs at each position. And we set our activation to softmax because really this is a classification problem. In the sense we're classifying what we want each digit to be in our output. And then we add this time distributed wrapper, and what that does is it basically makes essentially the same dense layer but on different input for each one of the outputs that we want. So in line 108 we compile our network, and actually this should be super familiar. We can use the familiar categorical cross-entropy that we always use when we're doing a classification. We can set the optimizer to atom, and of course you can try other ones. And then we set metrics equals to accuracy. And what this is going to do is actually tell us the digit by digit accuracy of this network, as opposed to the accuracy of the entire thing. So you might expect the accuracy to be how often did it get the right answer for the equation that we put in, but actually this is going to be how often do we get any particular digit correct. So lines 115 through 138, really what it does is it fits the model, and then it outputs some sample of the model data. So it's just kind of for fun, but we kind of want to see exactly what this network is outputting. So there's just a little bit of simple code that fits the network, and then at each step, so it fits it on one epoch at a time, and then at each step outputs what the network would have said on a random set of data. So hopefully that made sense. Let's try running the code. Here we are on iteration 22, and it actually got one of these digits, or one of these equations exactly right. So it knows that 3 minus 39 is negative 36. And it got the other ones wrong, but you can see that it's really close. It's almost close in a way that a human would be close, right? So it thinks that 49 minus 95,731 is negative 95,663, where the right answer is negative 95,682. So I think that's kind of amazing, right? This network almost feels like it's learning in some sense. Maybe if we're getting a little wild here, like a human being or something. And actually, I do know that if you run this network for longer, it gets higher and higher accuracy. In fact, it already has about 70% digit level accuracy, which is feeling pretty good. And one of the really cool things that you can do is you can take this code and you can modify it. So the simple modifications might be one to make this task a little bit harder. So you could add in multiplication, you could add in multiple additions, maybe put in parentheses. I think that would be a super interesting challenge to see how well the network can learn more complicated algebra. Some ways to improve the network are things that you might have seen in some of the previous videos that we've done. So I think a bidirectional network could be really effective here. If you make this thing more complicated, you might even want a multi-layer LSTM, although you better be patient if you put in multiple LSTMs as the encoding or the decoding. And then finally, what's really cool is you can take this exact code and you can apply it to other sequence-to-sequence translation scenarios. So if you have what's called a parallel corpus, if you have examples of sentences in, say, English and Japanese, you can feed them in 2 at a time into this network, and you can see if it can learn it. And in the Keras blog post, they actually do show that they can learn simple translations from English to French with exactly the same architecture and almost exactly the same code, which I just think is the coolest thing. In future videos, we'll get more advanced here. We'll maybe even learn how to go from images to captions and other kind of more exotic sequence-to-sequence translations. But for now, if you do anything cool, please put it in the comments, because I think there's so much to expand on in this framework.